Lesson 4.1, Exponential Functions. So we have two learning targets here, graphing exponential functions and using exponential functions to evaluate compound interest. Okay, so first we're going to talk about what an exponential function is. I've got an equation written here, the equation of a function, f of x equals a times b to the x. And this is what we're going to use for the equation of what we're calling exponential functions. Now, comparing a type of function that I know we're all very familiar with here, linear functions. So we have a linear function here, y equals 2x. 2 is the slope. That's the rate of increase. So it increases up 2 over 1, up 2 over 1. It has 0 as a y-intercept. So I know we're very familiar with linear functions. It has a constant rate of change, which is also known as the slope. Now, if we look here at this table of values, when x is negative 2, y is negative 4. When x is negative 1, y is negative 2. If we look at the difference in y values, so the difference between negative 4 and negative 2 is 2. The difference between negative 2 and 0 is 2. The difference between 0 and 2 is 2. The difference between 2 and 4 is 2. In between terms of a linear function, there's a common difference. And the key here is it's a common difference. It's the same difference every time, which is what generates this line or this function that increases at the same rate. Now with exponential functions, like this one here, we have y equals 2 to the x. Now notice how this is, it looks similar, but it's mathematically different. This is a base of 2 and an exponent of x. It's 2 raised to the power of x, where over here with linear, it's 2 times x. So 2 raised to the power of x is now considered to be an exponential function. And you notice it has a much different shape of a graph. Okay, and I've labeled some points here, or rather here on the graph, I've labeled some points. And then I've written those points in a table of values. Now, if we look at the difference between 1/2 and 1, the difference there between those is it's a difference of 0.5. The difference between 1 and 2 is a difference of 1. The difference between 2 and 4 is a difference of 2. And if I had continued this, next one would be a value of an x value of 3, a y value of 8. That's a difference of 4. The next one would have been 4 and 16. So then I get a difference of 8. So if we look at the differences between the y values, it's no longer a common difference, but there is something, there is a pattern here between these values. We're multiplying by 2, so 0.5 times 2 is equal to 1. 1 times 2 is equal to that. 2 times 2 is equal to that. 4 times 2 is equal to that. So we're not adding by the same number like we were doing here. Here we're adding by 2 every time. Here we're multiplying by 2 every time. So this is what's known as a common ratio. And that's exactly what this base is. The base is the common ratio. It's what we're multiplying by every time. 2 to the first power is just multiplying by 2 once. 2 to the second power is multiplying by 2 twice. 2 to the third power is 2 times 2 times 2. It's multiplying by 3 twice. So the common ratio, the base, is 2. That's what makes this exponential, is the fact that it has a base here that's being raised to an exponent. Now, as you can see that the x values are increasing and the y values are increasing. As x is increasing, y is also increasing. That behavior is known as exponential growth. exponential growth happens when the base, b, is bigger than 1. Now, a is just a coefficient that can be written in front of the exponential term. This is the exponential term right here, and a is a coefficient. And really all it is a vertical stretch like we learned about in section 2.6. It's just going to make the graph a little bit steeper or a little wider, depending on the value of a. That's just one of those transformations from 2.6. b, the base, determines whether or not we have exponential growth, or here's another exponential function, y equals 1/2 to the power of x. Now this is still considered exponential because we have a base raised to an exponent, and the variable is the exponent. And I want to make this clear. Just because a function has a base and an exponent does not make it exponential. See, in section 3.2, let me get a clean slate here. In section 3.2, we looked at functions like this, 3x to the fourth. That was called a polynomial function, even though it does have a base and it has an exponent. The difference here is the variable is the base and the exponent is a whole number. That's a polynomial function. Exponential functions, the base is a number and the variable is an exponent. That's what makes this exponential. And because the base, let me get down here, because the base is between 0 and 1, that's what makes this exponential decay. And you can see as the x values are increasing, the y values are decreasing. Okay, and the pattern here with the base is if we look at the differences in the y values, here we have a difference of 2, here we have a difference of 1, here we have a difference of 0.5. So what's happening is we're multiplying by 0.5 every time to get to the next value. Multiply by 0.5 to get to this value, multiply by 0.5. 0.5 is the same as 1/2, and that's where we get this base of 1/2. So this is just a brief introduction to what an exponential function is. An exponential function is a function written in the form a times b to the x, where b is some kind of a number either greater than 1, which makes it exponential growth, where as x increases, y is increasing, and it has not increasing at a constant rate like with linear, but it's increasing using a rate as a common ratio. So every y value is being multiplied by the same value. Now, exponential decay, still same formula, a times b to the power of x, but now b is a value between 0 and 1, which is causing the y values to decrease as the x values increase. So what we need to talk about as our first learning target is how to graph an exponential function. And we're going to look at both exponential growth functions and exponential decay functions. You graph them the same way, basically the same 3 steps. Now there's a characteristic of both of these graphs that is similar to a characteristic that we saw back in chapter 3, section 3.6, when we graphed rational functions. Looking at this exponential growth function here, for example, if you notice, the graph, if we're moving from right to left, the graph gets closer and closer and closer to the x-axis, but never actually touches the x-axis and never goes down beneath or below the x-axis. And remember, there's a word for that kind of behavior where a graph approaches a line but never crosses that line. It's an asymptote. So there is a horizontal asymptote right here at 0. There's also a horizontal asymptote here for exponential decay. There's a horizontal asymptote at 0. So if we start to incorporate some of the ideas and techniques from section 2.6, transformations of functions, the graph can start to move up or down with a vertical shift. The graphs can move left or right with a horizontal shift. And depending on the value of a here, we can also have vertical stretch or vertical compression. So for example, if I put a +1 outside of the function here, that would result in a vertical shift, which moves the graph up 1 unit. So then the horizontal asymptote and the graph would move up 1 unit. If I put a -5 right here outside of the function, that would result in a vertical shift down 5 units. So the horizontal asymptote and the graph would shift down 5 units. So the first step actually is to, well, let me actually bring this up here. When graphing exponential functions, first step is to locate the horizontal asymptote. Normally it's at 0, unless there's a vertical shift, which moves the horizontal asymptote up or down by that value. The next step is to locate your y-intercept, and we've done that plenty in this course already. You find the y-intercept by letting x equal 0. Third thing is to plot some additional points, and that's as easy as choosing some x values, plugging them into the function to find the y values. So, as an example, we're going to graph the exponential function f of x equals 2 to the power of x plus 1. Now, it's an exponential growth function because the base is a value that's bigger than 1. So we expect the graph to resemble that of an exponential growth function, which has that kind of a shape like that. So we expect our graph to look something like that, something similar to that. So step 1 is locate the horizontal asymptote. Like I said, typically it's here at 0, unless there's a vertical shift. In this case, we're moving up 1 unit, which also moves the horizontal asymptote up 1 unit. So the horizontal asymptote is the line y equals 1. Now step 2 is to graph the y-intercept. So the y-intercept, I'm going to make a table of values here. The y-intercept we find by letting x equal 0. So if we plug a 0 in for x, we get 2 to the power of 0 plus 1. Now, 2 to the power of 0, anything to the power of 0 is 1. So 2 to the 0 is 1. 1 plus 1 is 2. So 0, 2 is our y-intercept. Now we need a couple of extra points. So I require a total of 3 points on these graphs. Your y-intercept here counts as one of those points, so just need 2 others. I'm going to let x equal, whoops, let's do 1 first, x equal 1. So now we plug in a 1 for x, so that would be 2 to the first power plus 1, which is 3, so 1, 3 is on our graph. Now when x equals 2, it's 2 squared plus 1, which is 5. So 2, 5. Okay, and that's the graph of the function 2 to the x plus 1. Now the domain of this graph, and the domain of this function rather, the domain of this function is all real numbers. We can use any negative x value as an input, and we can use any positive x value as an input. So the domain is all real numbers. Now the range, if we're looking at the y-axis, the range on the y-axis here, it does go up to positive infinity, but as far as the lowest bound, or the least number in the domain, it approaches 1. So if we're looking at a y value of 1, the graph y values are approaching 1, and they're getting closer and closer to this line, which is y equals 1, but it never actually equals a y value of 1. And so the way we write this domain, since there's an asymptote at 1, it's from 1 to infinity, not including 1, so we put a parenthesis there. So let's look at another one. 2 times 3 to the x plus 1 minus 1. So as far as the transformations go that we talked about in section 2.6, we have a vertical shift down 1 unit. We have a horizontal shift, because this is inside the function, so it's moving to the left 1 unit, and then this results in a vertical stretch. We follow the same 3 steps. We locate the vertical asymptote, which is now -1, because the graph has moved down 1 unit. So when we're graphing this, we'd have our horizontal asymptote at -1. And then when we want to find the y-intercept, we let x equal 0. This x is going to equal 0. So then the equation would be, or the expression would be 2 times 3 to the 0 plus 1 minus 1. Now here, 0 plus 1 is 1, so 3 to the first power. 3 to the first power is 3. 3 times 2 is 6, and then 6 minus 1 is 5. So 0, 5 is our y-intercept. Now you can sense the domain, and I'm going to say this probably a couple times in this lesson and in subsequent lessons, the domain of any exponential function, whether it's growth or decay, the domain of any exponential function is always all real numbers. You can plug in negative values to exponential functions. You can plug in any positive value to exponential functions. So the domain is all real numbers. What that means is I could plug in any value I want for x, and typically, students would choose 1, 2, and 3 here. What is going to happen, though, the reason I probably wouldn't is for x equals 1, we're going to be way up here. For x equals 2, we're going to be way up here. Those are going to be pretty high y values. So I'm actually going to go the other way. Instead of using 1, 2, and 3, maybe x equals 1, but beyond that, I'm going to use negative 1 and negative 2. So when x equals 1, we have 2 times 3 to the 1 plus 1 minus 1. Now here, 1 plus 1 is 2, 3 squared is 9, 9 times 2 is 18, 18 minus 1 is 17. So 1, 17. Like I said, you're getting pretty high off the graph there. Now for negative 1, we're going to have 2 times 3 to the negative 1 plus 1 minus 1. So negative 1 plus 1 is 0. 3 to the 0 power is 1. 1 times 2 is 2. 2 minus 1 is 1. So negative 1, 1. And then when x equals negative 2, we have 2 times 3 to the negative 2 plus 1 minus 1. So here, negative 2 plus 1 is negative 1. 3 to the negative 1. And I want to talk about this for a second. So 2 times 3 to the negative 2 plus 1 minus 1. Right here, negative 2 plus 1 is negative 1. So 2 times 3 to the negative 1 minus 1. 3 to the negative 1 power is not negative 3. You need to recall some of the properties of exponents that you learned in Math 1010. Negative exponents do not produce negative outputs. 3 to the negative 1 is the same as 1 over 3 to the positive 1, or 1/3. So what we have here is 2 times 1/3 minus 1, which is 2/3 minus 1, which is negative 1/3. So when x equals negative 2, we have negative 1/3, which is about right there. So we have a couple of points right there. You can see it's a little bit steeper. It's been vertically stretched. First of all, because we had a vertical stretch right there, but also the bigger the base, the steeper the increase also. So that's another exponential growth function. Okay, here's an example of exponential decay. We know it's decay because the base is 1/2. Any base between 0 and 1 is going to result in exponential decay. And if you recall the shape of a decay graph, y values decrease as x values increase. So the graph's going to look something like that. Now we have a vertical transformation, up 1 unit, and we have a horizontal transformation, right 1 unit. First step is to locate the horizontal asymptote. And because of this vertical transformation up 1 unit, that's going to move the vertical asymptote, the horizontal asymptote up 1 unit. Now to find a few of our points here, we need the y-intercept, so x equals 0. we're going to have 3 times 1/2 to the 0 minus 1 plus 1. So we have this same situation now. 1/2 to the 0 minus 1 is 1/2 to the negative 1 power. When you have a fraction raised to a negative exponent, you invert the fraction, or you find the reciprocal of the fraction and change it to a positive exponent. So 1/2 to the negative 1 is the same as 2 over 1 to the positive 1, which is 2. So then this turns into 2. 2 times 3 is 6. 6 plus 1 is 7. So the y-intercept is 7. Now, if x equals 1, then we have 3 times 1/2 to the 1 minus 1 plus 1. So here we have 1 minus 1, which is 0. 1/2 to the 0 power is 1. 1 times 3 is 3. 3 plus 1 is 4. So 1 comma 4. Okay, 2, if x equals 2, we're going to have 3 times 1/2 to 2 minus 1 plus 1. So 2 minus 1 is 1. 1/2 to the first power is 1/2. 3 times 1/2 is 3/2. 3/2 plus 1 is 2.5. And we can finish the graph like that. Now, I skipped domain and range on part B, but let's pick it up here again on part C. Domain of any exponential function is all real numbers. Range, if we're looking at the y-axis, the y values are going up to positive infinity, but the lower bound for the y values are approaching this line, y equals 1, but never actually reaching this line. So the range is from 1 to infinity, but not including 1. So that is our first learning target, graphing exponential functions, and it boils down to 3 steps. First, find the horizontal asymptote, and that's located using vertical transformations. If there is no plus or minus some number here outside of the function, then the horizontal asymptote is on 0. Okay. Second thing you do is let x equals 0 to find your y-intercept, and then you just need a couple of other points, and just plug those x values into the function to find the y values. Okay. Second learning target is an application of exponential functions called compound interest. Now, this is not going to be the only application we study. It's just an application we're going to study here in 4.1. We're going to see a few more later on in the chapter. So, compound interest. Now, I want to illustrate the difference, or try to explain the difference between a simple interest situation or a compound interest situation. So, first of all, interest is money that you get from an investment. So, if I invest $1,000 and there's an interest rate of 5%, I'm going to get 5% of 1,000. That's interest. Simple interest is only the interest that's calculated on the principal balance only. Now, the principal balance is what you initially invest. So if you invest $2,000, then $2,000 is your principal investment. So if you invest $2,000 into an account yielding 5% simple interest, then the account will earn 5% of $2,000, which is $100. It's going to earn $100 per year. So the interest is always going to be 5% of the original principal balance, which is $2,000. So it's $100 per year interest. So if you invest for 10 years, you're going to get $100 per year. So you'll earn $1,000 in interest. That's simple interest. It's interest that's calculated on the principal balance only. So you can see here, year 0, which is the starting year, the amount is $2,000. but after 1 year, you're going to have $2,100. After 2 years, you're going to have $2,200. 3 years, 23. So it's increasing at a rate of $100 per year. It's increasing at the same rate. This is linear growth. If it's increasing by adding the same value every time, that's linear growth. That's what we talked about here a few minutes ago, the difference between linear functions and exponential functions. The formula for simple interest is the principal balance, or the principal investment, and then 1 plus the interest rate. Now, what we actually need to talk about here is compound interest. And here's the difference in compound interest. It's interest on the principal and past interest returns. So for example, what we have here, suppose you invest $2,000 into an account that yields 5% interest compounded. Whoops, raises up here. Here we go. That's compounded every year. So after 1 year, 5% of 2,000 is $1,000, or $100 rather. So your total is $2,100. But now the interest is going to compound or be accrued on $2,100 after year 2. So it's 5% of $2,100, which is $105. So the increase after year 2 is $105 rather than $100. So now you have $2,205. So for year 3, the interest is going to be calculated based on this increased principal. So $2,205, 5% of that is $110.25. So now after year 3, you have $2,350.25. So you can kind of see it's not a significant difference in growth. Year 1, year 2, year 3 compared to year 1, year 2, and year 3 over here with simple interest. But that's because we're dealing with relatively small investments, $2,000 and a smaller interest rate. But you can see it is more. And where it starts to have a significant difference is the longer you leave it in. If you leave this in for 10 or 20 years on simple interest, you're still only going to increase at $100 per year. 10 or 20 years of compound interest is going to see significantly more growth. So looking at this and trying to derive a formula, after 1 year, the interest was $100, so the amount was $2,100. That was the principal plus the interest, which is 5% of the principal. So 2,000 plus 5% of 2,000, which is where the $2,100 came from. But written out, since 2,000 is common to both sides of this expression, if you factor out the 2,000, you have 2,000 times 1 plus 0.05. Now, for year 2, this becomes your principal. So this increased amount is the principal on which you add the interest onto it. So we start with this principal, and then we add 5% of that principal. And now this principal is common to both sides of this expression. So if we factor that out, we end up with 2,000 times 1 plus 0.05 squared. Now, I'm just showing this more to maybe help you understand. What I really want you to pay attention to is some kind of relationship between this formula and number of years. And you've probably already seen it. The exponent here is just the number of years that you've invested. Now this, after year 2, becomes the principal investment for year 3, and then on top of that you add 5% of that principal investment. Now this is a common term on both sides of the equation, so if you factor that out, you're left with this expression, 2,000 times 1 plus 0.05 to the third power. So again, this exponent is the number of years it's been invested. Another thing to pay attention to is this is no longer linear like with simple interest. Simple interest was a linear function where it increased by the same value. It increased by $100 every year. So it's adding the same value, which is a common difference. Here, we're multiplying by the same value, 1.05 every year. And so this is increasing using a common ratio. This is an exponential function. So compound interest here, 1 plus r to the power of t, the base is 1 plus r, where r is the rate, and this needs to be as a decimal, not a percent, so a decimal. And t is the number of years. This is exponential, and it's exponential growth because 1 plus the rate is going to make this a value bigger than 1, which is why this results in money growth. So this is a basic formula for compound interest if it's compounded just every year, once a year. What we're going to see, and what is perhaps a little more common, is if the interest is compounded more than once a year. So they could compound the interest twice a year. So for example, if the interest rate was 5%, but it's compounded twice a year, then each time it compounds, it's going to be half of that because it's happening twice a year. So half of that 5% would be 2.5%. So the first time it compounds in the middle of the year would be 2.5%, and then at the end of the year it compounds at another 2.5% to equal your 5%. So let's say so in that case it would be twice a year. So if we're saying n times per year, then this n would be 2. So then it's your rate divided by 2. Now the exponent is the number of times it compounds. So if it compounds twice a year, then it's n times the number of years, and that would tell us how many times the interest is going to be evaluated. So if it's compounded, let's say it's compounding monthly, then n times a year, if it's compounding monthly, is 12. So your interest rate is going to be divided over 12 compounding cycles because it's 12 times a year. So it's interest rate divided by 12. But then the number of times it compounds is the number of years multiplied by 12 because it's 12 times per year. So this is the compound interest formula we're going to use, assuming that the interest is going to compound more than once a year, let's say n times per year. And just to be clear on what these values all mean, P is your principal investment, R is your interest rate as a decimal, not as a percent, N is the number of times per year you're compounding, and T is the number of years of the investment. And A is just the future amount, the amount at so many years. So as an example here, suppose we invest $10,000 into an account that yields 4% interest compounded monthly. How much money will you have after 20 years? So the principal investment is $10,000. Time, T, is 20 years. N is compounding monthly. That means it's 12 times a year, so N equals 12. And then the rate is 4%, but remember you have to use a decimal in this formula. You can't use a percent in a formula. You have to use a decimal. All right, so now putting this all into our formula, the amount after 20 years is our principal investment, 1 plus the rate divided by n, which is 12, and then the exponent is going to be n times t. And from here on out, it's a calculator problem. This is something that you would type into a calculator. Your scientific calculator can handle this. I would suggest that you don't try to type the whole thing in at the same time unless you're very comfortable using your calculator in parentheses and exponents. I'd recommend you figure out what this value is first. So this is 1.00333 repeating. And then 12 times 20 is 240. Next, I would take this and raise it to that power, which is 2.2226. And then I would times that by 10,000, which is right around $22,000, 226. Now I say right about because I did a little bit of rounding with this number here. So you can see we started with $10,000. It's compounded monthly for 20 years. The amount grew to $22,226. So it more than doubled in those 20 years. So this is an example of how you would use the compound interest formula. Now, things that are going to have a profound effect on the rate of money growth is not actually the number of times that it compounds. If I had switched this to compounding daily here rather than compounding monthly, if it compounds every day, that's 365 times a year, so n would be 365. So your initial thought might be, well, that's going to result in a huge increase of money it actually doesn't increase the total value as much as you would think. The number of times that you're compounding the interest doesn't have much of an effect. It will increase it slightly. What's going to make the biggest impact on this formula, money growth, is either you leave it in there for a longer period of time, so the amount of time, or you simply have a higher interest rate. So what you will see as examples in your textbook is where you may compare the growth between different compounding. So compounding monthly, which would be n equals 12, or compounding daily, which is n equals 365, or compounding quarterly. They may use the phrase quarterly, which is 4 times a year, so n would equal 4, just to see and compare how changing the compounding cycles affects money growth. But that should finish up learning target number 2, compound interest, for the section 4.1.